Hey calculus friends, today we are going to be talking about an application of integration, which is volumes of rotational solids. In our text, this is section 6.2. We're going to divide it into 2 days, so this is section 6.2, day 1. All right, so first I'd like you to take a look at some of the pictures that we have here on the screen. On the left-hand side, we just have some regular cylindric solids there. We have the cylinder or the circular cylinder or the rectangular box, all of which kind of fall into the cylinder category, where we'd be looking at finding the volume of those objects by finding the area of the base and then multiplying it times the height. And so those are kind of pretty obvious when we think about volume. But then when we look in the main body of the notes here, what if we're trying to find a volume of a solid where the height is changing at any given time because of the nature of the shape? So when we try to find the volume of the solid, we have the same problem that we had when we try to find the area under a curve. We know volumes of solids are typically found by area of the base times the height, just like I discussed. But what if the solid we're working with is not a cylinder by definition? So the first thing I want you to look at is how in the picture on the left there, they've intersected our volume or our solid here and sort of made what looks like a slice of bread here and there. And that's a plane region that we would call a cross section. So if we could find the area of that cross section and then multiply it by the distance along the x-axis, which technically if we laid that cross section flat, that would be like the height, then we'd be finding the volume. And as we know with integrating, if we take the limit of a whole bunch of cross sections all added together, that Riemann sum, then that is going to give us our volume of our rotational solid, okay? So we've got this definition of volume. Let S be a solid that lies between x equals A and x equals B along the x-axis. Those are going to be our limits of integration. Then if the cross-sectional area of S in the plane P of x through x and perpendicular to the x-axis is A of x, where A is a continuous function, then the volume of S is going to be equal to the limit as n goes into infinity of the sum from 1 to n of the area of basically a slab times the height of the slab, right? Because base times height, or area of the base times the height, would give us volume. And this translates for us in calculus as the integral from A to B, A being that distance along the x-axis, of the area of a cross-sectional slab times the height of the slab. So right here, this part right here, this is the area of a cross section, and this d of x, remember, is it's representative of our height in our integral. So for our first example, we want to find the volume of the solid that's obtained by rotating a region bounded by the given curves and the specified line. We want to sketch a picture of the region, the solid, and a typical disc or washer. And I think this is going to make a lot more sense when we look at our first example. Now I have this note here that I want to call attention to because we're going to see it both ways. We're going to see where it's rotated around the x-axis and where it's rotated around the y-axis. And so we'll do it both ways and you'll see. But in this case, we are rotating about the x-axis. So it's going to be easier to integrate with respect to x, which is what we're used to doing. Okay, now if we are going to integrate with respect to y, it's no different. It's just a change in variable, and it's just kind of a flip in perspective. But again, we'll do an example like that in a little bit. So the first thing that we need to do here is we need to sketch a picture of what we're looking at. So I'm going to draw a coordinate plane. And my curve is y equals 2 minus 1/2 x, which, as we know, is just a diagonal line. It has a y-intercept of 2 and that it has a slope of -1/2. Switch colors here. So if I have a y-intercept of 2, and then I have a slope of -1/2, that means that I'm going to be going down 1, right 2 as I sketch more points on my curve. So down 1, right 2, down 1, right 2, down 1, right 2. That's going to give me a line that looks something like this. All right. And then it says y equals 0. So that's going to be my x-axis, right? X equals 1 and x equals 2. Well, here's x equals 1. Here's x equals 2. So really what I'm looking for is this little piece right here, but I'm rotating it about the x-axis. So this is where it becomes the volume of a rotational solid. So I'm going to sketch a second picture just so that we can kind of visualize what's actually going on here. So here's my little chunk of area right here, I guess we'll call it, right, from 1 to 2. And if I'm rotating it about the x-axis, you have to kind of envision that this is being spun around. This little piece is being spun around. And so it's going to create something that looks like this, right? Okay, so that is what we would call our cross section, right? And here is x equals 1, and here is x equals 2. All right, so what we have to see when we look at this picture is that our cross section is a circle. And we know from past experience that area of a circle is found by taking pi times the radius squared. So that's going to be the area part of our integral. But we need to figure out what our radius is. Well, when we look at our picture, here we've got the circle, right? And so the radius would be this distance from here to here. Well, again, our radius is not constant. It's changing as we go from x equals 1 to x equals 2. But the radius is equal to that function y equals 2 minus 1/2 x. So our radius is 2 minus 1/2 x. So now our volume, we can go ahead over here now and we can come up with a volume function. Our volume is going to be equal to the integral from x equals 1 to x equals 2 of the area of a cross section, which is that circular disc that we drew, and we know that the area is pi, times our radius, which is 2 minus 1/2 x squared. That is a quantity squared, right? Our radius is squared, times the height, or the distance along the x-axis, which is our change in x, or our dx. Okay, so again, this part is the area of the cross section, and this part is the height of the cross section. If we were to lay a circular disc, or a circular, they call it a disc, flat, okay? So the calculus basically is done, thinking through setting this up. Now we just have to work, with the math that we know to solve this problem. So basically we have to do this integration. Well, when we look at the function that we're dealing with, right away I can say, well, we can pull that pi out in front of the integral. And so I might do that first right away. So volume is pi times the integral from 1 to 2 of 2 minus 1/2 x quantity squared dx. Okay, so now here's the problem. I'm going to have to do a u substitution because I don't have an integration trick for something that looks like this. So I'm going to let u equal 2 minus 1/2 x. okay? So I would have u squared when I plug that in. So then my du would be the derivative of that. The derivative of 2 would be 0. The derivative of negative 1/2 x would be negative 1/2 dx. And again, I'm trying to make it match my original function. So if I want to get rid of that negative 1/2, because that's not like a coefficient in front of my 2 minus 1/2 x quantity squared, I'm going to multiply both sides by negative 2. So negative 2 du will equal my dx. Okay, so now I've taken care of this part. Dx is equal to negative 2 du, and I've taken care of this part. This is just going to be u squared. So now my volume is going to be pi times the integral from 1 to 2 of u squared times negative 2 du, right? Replacing my dx with negative 2 du and my 2 minus 1/2 x with u. And again, then I can pull that negative 2 out in the front with the pi. So this will be negative 2 pi times the integral from 1 to 2 of u squared du, which is going to be equal to negative 2 pi times, now when I integrate this, u squared is going to integrate to 1/3 u cubed. So 1/3 u cubed, right? And actually, I apologize. I'm going to take a step back here. I know it's 1/3 times whatever u is cubed. So I'm going to go ahead just for the sake of simplicity here, and I'm going to go and I'm going to plug my u back in, which is 2 minus 1/2 x cubed. Okay, that evaluated on the interval from 1 to 2. Okay, so at this point right here, we're just going to use the fundamental theorem of calculus and evaluate, right? This is going to be, so our volume is going to be equal to, we've got that negative 2 pi over 3, right? Because negative 2 pi times 1/3, negative 2 pi over 3 times 2 minus 1/2 times 2 cubed minus negative 2 pi over 3 times 2 minus 1/2 times 1 cubed. Okay. And if you plug that all into your calculator and you do the math here, what you should end up with for your answer, and for the sake of time, I'm just going to give you the solution here, is going to be 19 pi over 12. And I left my answer in terms of pi. That's how you will see it most of the time. But if you wanted to know what that was as a decimal, of course, you could just plug that into your calculator and look at it that way as well. One thing I do want to point out when you go back and you do the math here is you do have this minus a negative right here, which chop chop is going to become plus a positive. So make sure you do go back, follow through with the math, and make sure that you end up with 19 pi over 12 as your final answer. So we are resuming with example 2. And as I mentioned previously, when you are rotating around the y-axis, or x equals a number, because those would both be like a vertical line, in that case, it's going to be easier to integrate with respect to y. So when I look at example 2, the lines that I'm working with are y equals natural log of x, y equals 1, y equals 2, x equals 0. And it says right here about the y-axis. Okay, so there's my clue that I want to integrate with respect to y, which means that I need this equation right here to be x equals something with y. Well, lucky for me, that's easy enough to change, right? If I've got y equals natural log of x, and I just want to raise both sides to the power of e, the e and the ln cancel out, so I get x equals e to the y. So y equals ln x equals e to the y. Those are the same function, just written two different ways. Okay, now my next job is let's take a look at a picture of what we have going on here so that we can kind of visualize what's happening. So here's my coordinate plane. And I know what y equals ln of x looks like. I know what a natural log function looks like. It looks something like this, right? Okay, so there's my x equals e to the y, or y equals ln x, however you want to think about it. And then I'm rotating about the y-axis, right? So I'm rotating about that vertical line there. And my kind of limits of integration are going to be from y equals 1 to y equals 2. So if I draw those in, then I have, and if I shade that in, kind of the shape that I'm going to be rotating around my y-axis, it almost looks trapezoidal in a way, but it's got that little curve on the edge from my logarithmic function. Okay, so that is what I am going to be rotating. So now let's take a look at the rotational solid that is produced when I do that. So once again, here's my y-axis. Here's my x-axis. So I've got my shape, which looks something like that, right? This is the curve right here on the edge. This is the y equals ln x. And if I rotate this around the y-axis, then it's going to spin like this all the way around. And the same thing is going to happen down here. It's going to spin all the way around. And so I end up with something that looks sort of like a bowl, I guess. And this time, since we're integrating with respect to y, our cross sections are going to look horizontal rather than looking vertical. But if I shade this in again, you can see that once again, my cross section is going to be a circle. And that's important because we always need to be able to create a function for the area of the cross section of our solid. Okay, so there's my shape that I'm going to be rotating, or that I'm going to create by rotating my solid that I'm going to create by rotating around the y-axis. So once again, I know that my cross section is a circle, and I know that area of a circle is pi times the radius squared. So then we just have to decide, well, what is our radius? And again, we know that this right here is y equals 1, and this right here is y equals 2, right? There's our kind of our height of our volume solid. So our radius then, once again, just like before, is going to be our function that we started with, which is our y equals ln of x, or in this case, since we're integrating with respect to y, our radius is going to be equal to e to the y. All right, so I'm ready to create an equation for my volume. So my volume is going to be equal to the integral, and this time we're integrating with respect to y, so the limits of integration on my y-axis are going to be from y equals 1 to y equals 2. Now I need the area of our cross section, so it's going to be pi times my radius, and my radius is e to the y squared, times my height, which is dy. And I can do a little bit of algebraic simplification. I just have a good old-fashioned exponent rule. I have a power to a power. We know that when we have a power to a power, we multiply our exponents. So this is going to be the volume from 1 to 2 of pi times e to the 2y dy. And I can go ahead and I can pull my pi out in front of my integral. So now I just have to integrate this. Okay, now you could probably do this without a u sub in your head, because you know that the integral of e to the u is e to the u, right? But then we have to multiply by chain rule by the derivative of our u, so we have to undo that, but it might be easier just in this case, if we're a little bit rusty perhaps, to show the work of the u substitution. So for this problem, I'm going to let u be my exponent, which is 2y. So then du would be 2 dy. And if I just want dy, then I would have to divide by 2. Right, so now I've got a representation for my dy. That's going to be du over 2. And then e to the 2y just becomes e to the u. And I can take that division, that du over 2, I can move that 1/2 out in front of the integral. So then I will have pi over 2 times the integral from 1 to 2 of e to the u du. Well, now this is easy because the integral of e to the u is e to the u, right? So my volume is going to be equal to pi over 2 times e to the, but I'm going to plug what u is back in. So it's e to the 2y, evaluated from y equals 1 to y equals 2. So then I can just go ahead and I can plug this back in. Fundamental theorem of calculus time. So this is e to the 2 times 2 power minus pi over 2 e to the 2 times 1 power. And so then I get pi over 2 e to the 4th minus pi over 2 e squared. And you could write this a lot of different ways. If you wanted to, you could factor out a pi over 2 e squared. So then you just have e squared minus 1. You could leave your answer in that form. Or if you wanted to grab your calculator and just type this in your calculator now, you should get 74.156. So either of these right here would be an acceptable form for your answer. These examples are intense, are they not? All right, we saved the best for last here. Example 3, we've got y equals x cubed, y equals x is greater than or equal to 0, and it says about the x-axis. So again, if we are rotating about the x-axis, then we are going to be integrating with respect to x. Which means we want any equations that we're working with to be y equals, which they already are. So we don't have to do any manipulations of our equations. So that helps, that makes it easier. All right, let's start with a picture just like we always do so we can kind of visualize what we're working with here. So here's my coordinate plane. And I know y equals x cubed, that is my standing snake shape. So that is going to look something like this. And I know y equals x, that's just a diagonal line that goes through the origin with a slope of 1. Okay. So that looks something like this, right? So I have this itty bitty little thing right here. I don't know, it looks kind of canoe shaped to me. It's got a straight line for the top, but then it's got kind of a curvy bottom because of the y equals x cubed. That is the shape that is going to create my rotational solid, and I'm going to be rotating it about the x-axis, right? And I'm going from x equals 0 to right here, which is x equals 1, because I know that both of my lines have 1, 1 as a point. Y equals x cubed contains 1, 1. Y equals x contains 1, 1. So that is where they are going to be intersecting each other. And that was a little bit different in this problem. In previous problems, those were given to us. Okay, but in this problem, we kind of had to figure that out for ourselves, that our limits of integration are going to be from x equals 0 to x equals 1 just based on where our two curves intersect each other. This is the first time we've had two curves instead of just one curve. So now let's think about what this is going to look like when we rotate it about the x-axis. So second picture down here. All right, so I'm going to blow this up a little bit just so that we can kind of look at it a little bit more carefully. So we have this shape that's got a flat top like that, and then it's got kind of a curvy, looks sort of like a banana, I guess. And if I'm going to be rotating this around the x-axis, then it's going to look something like this. Okay. But it's not going to be filled in because you notice here that we've always got this kind of hole in the middle because our shape doesn't go all the way down to the x-axis. So this is going to create what we call a washer. Right? It's not a disc, it's a washer because it's got a hole in it. So as we color that in a little bit better, you can kind of see that washer taking shape that is created when we rotate this around our x-axis. And again, out here in our perimeter, we have a washer too. So this is a little bit different than the previous problems that we did because in the previous problems we had discs and now we have a washer. So our cross section is a circular washer. And remember, our job is we have to come up with an equation for the area of that washer. Well, if you think about it, a washer is really just a disc with the center cut out, right? So the area of a washer would really be the area of the whole disc, right? Which would be pi r squared, but this would be of the outer radius or the outer function. And then we would just have to subtract off the inner circle, which would be pi r squared of the inner. Okay, so that's going to be our area. So it's a little bit more complicated, but yet we can figure it out because we know that the radius of our outer function is going to be, hang on, let me switch colors here. The radius of our outer function is that line y equals x. So our radius is x for our outer function. And then the radius for our inner function, which again our inside of our washer, comes from the line y equals x cubed. So here, sorry, that's hard to see, the radius is x cubed. All right, so I think we're ready to create a volume equation. So we know that our volume is going to be equal to the integral, and we figured out our limits of integration have to be where these two functions intersect each other. So from x equals 0 to x equals 1. And our area is going to actually be the subtraction of two areas. So it's going to be our first area, our outer disk, which is pi times the radius squared, minus, and we have to subtract off the hole in the middle for our washer, which is going to be the smaller circle that's created by pi times x cubed squared. And then if we were to drop one of these washers flat, then our height would be our dx. All right, so now we can just do some calculus, right? Some math. So the first thing I'm going to do is factor that pi out in front of my integral. So I've got the integral from 0 to 1 of just x squared minus, and power to a power we multiply, x cubed squared is x to the 6. So x cubed minus x to the 6 dx. Oh, we don't need to do any u substitution here. This is just a polynomial. So we know that our volume is going to be equal to pi times the integral of x squared is going to be 1/3 x cubed, and the integral of x to the 6 is going to be 1/7 x to the 7th. And we are going to be evaluating this from x equals 0 to x equals 1. So then we just go ahead and we plug in our values. Well, we've got pi times 1/3 times 1 cubed minus 1/7 times 1 to the 7th minus pi times 1/3 times 0 cubed minus 1/7 times 0 to the 7th, which all of that goes to 0, so we can just ignore that. So we end up with pi times 1 cubed is 1 times 1/3 is 1/3. 1 to the 7th is 1 times negative 1/7 is negative 1/7. We create a common denominator here, turn them both into 21. So we end up with 7/21 minus 3/21, which gives us an answer of 4 pi 21 for our volume.